Hi students, today we are going to talk about Le Chatelier's principle. Now the picture below shows you country A and country B and a border between the two. And the caption says, when country A citizens feel overcrowded, some of them will emigrate to country B. So before the emigration, let's take a look at country A and country B. So country A has a lot of citizens and country B doesn't have very many. So we can imagine that country A is the US and country B is Canada with not very many people. And before any immigration happens, they are both at equilibrium, which means that they have a constant concentration of people, and the rate of movement of people from country A to country B is the same as a rate of movement of people from country B to country A. So, we're taking a look at what happens when all of a sudden the population of country A gets kind of crazy and some people are looking for a little more space. Well, that's a disturbance in the equilibrium. So what happens is that people from country A are going to look over the border and say, wow, there's a lot of space up there. So I think I'm going to move up there. And that brings us to the next slide. And the next slide says, however, as time passes, immigration will occur in both directions. So before that happens, people from country A move to country B, and that's not equilibrium right then because we have more reaction in the forward reaction rate than we have in the reverse reaction. So we have a little bit of ruffling of feathers over in country B because the population says, whoa, we got to build new houses for all of these people and new schools and whatnot. And so country A and country B have to get used to the new situation. So that brings them to a new equilibrium. So the caption says, time passes after the emigration from country A to country B, and we come to constant concentrations or constant populations. And then we have a few people going from country A to country B, but about the same amount of people going from country B to country A in the same amount of time. So we reach a new equilibrium there. So what's happening here is when you're at equilibrium and then something disturbs the equilibrium, a new equilibrium will be found after an amount of time. So then we have country A and country B with a new equilibrium, and then all of a sudden something happens in country B. Like maybe there is a big polar vortex and there is lots of rain and snow and ice, and people in country B say, oh my goodness, like I can't handle the cold anymore. And that equilibrium is disturbed because people from country B start moving over into country A. And country A says, whoa, we weren't used to all these people, so we gotta take them in and build some houses for them, get their kids in school, a little bit of a strain on the medical system, all of those things. But country A will go ahead and respond in order to minimize what we call this disturbance, and eventually we'll reach a new equilibrium. So the point is that when there's a disturbance in the system will respond in order to find a new normal. And this is Le Chatelier's principle. So Le Chatelier said if a system is at equilibrium and the equilibrium is disturbed somehow, the position of the equilibrium will shift in order to minimize the disturbance. So the system will take care of the disturbance in order to reach a new normal or a new equilibrium. And when we're talking about reactions, how we can disturb the equilibrium is by changing the concentration of the reactant or the product, either way, by changing the pressure or the volume, by changing the temperature. And then at the bottom, it says that your new concentrations of your reactants and products will be different, but the equilibrium constant, which is K, will be the same. So the system will shift to come to a new equilibrium where the ratio of products to reactants is the same. So remember, K is equal to products divided by reactants. It doesn't mean that the concentrations of products and reactants will be the same as before the disturbance, but the ratio of the two will allow us to keep the same K. So if your K was originally 1.5, the concentration of products and reactants will adjust somehow to keep the K at 1.5. So what on earth am I talking about? Well, let's take a look at this reaction right here, where we have N2O4 gas going to a couple of NO2s. Now, our system was originally at equilibrium. So if you guys look at the graph at this portion right here, we are at equilibrium here. And this is just showing you the very end of an original graph. And say we had something like this, okay? So it would look back here, if we were to back up the graph, would look very much like one of the graphs we saw back here. Like this right here. But on our new graph, all we're seeing is that the graph is starting right here at the original equilibrium. You're not seeing this back here. I drew that back there. So just so you get an understanding of where this graph is starting at. Okay, so right here, we've let the reaction go and we've let it reach equilibrium. And what we're going to do is we're going to disturb the equilibrium by adding in some reactant. So we pour some of the reactant in and the system goes, oh my goodness, I have too much reactant. What do? I've got to minimize this disturbance somehow. And the way it does that is it says if there's too much reactant, let's make some what? Let's make some product. And you can see right here, let me switch to red. You can see how we've got our reactant there and how you're dumping a bunch of it in because you get an increase in concentration right there. So you put a bunch of your reactant in there and you see the concentration spike, and then the system freaks out and it's like, what are we going to do with all this extra reactant? Well, let's make some product with that. And you can see how the system is slowly adjusting right here and making some more product. And it's going to do that, so it's going to make some product and it's going to get rid of some of that new reactant. and it's going to do that until we reach a new equilibrium. Now, you guys, you'll notice that you have a Q equals K up there. Q is exactly the same thing as K. We have the concentration of products over the concentration of reactant. But Q is when you're not at equilibrium. And then when you reach equilibrium, we say that that is K. So you'll notice at equilibrium it says Q equals K, and then when we're not at equilibrium, Q does not equal K, and when we're at equilibrium again, Q equals K. But I don't want you to worry about Q, because you don't have to worry about that unless you're going to go on to General Chem 1A and 1B, and then you'll do some more work with Q and K. But for us, we're just going to work with K right now. Okay, so I want to give you just some made-up math for the behind the scenes what's going on with K here in order to keep K the same. So remember, you guys, that K is equal to the concentration of products over reactants. And here our product is NO2. And the coefficient right there is 2, so that is the exponent that we put there. And then the reactant is N2O4. Okay, so I'm going to just make up a K for this reaction. Let's just say that K is equal to 4. Now, it is not 4 for this reaction. I just made that up so that the math is a little bit easier. And I need a little bit more room, so I'm going to shift us down here. Okay, so at equilibrium 1, let's say that K is equal to 4. Now, I need a concentration of product over a concentration of reactant. And if we just have a whole number, we know that we have a denominator of what? Of 1. Okay, so we're going to disturb this whole thing. We're going to dump some reactant in there. The reaction system is going to freak out, and it's going to take care of that extra reactant by making some product. And then we're going to come to K again. And K is going to want to stay at 4. But as you guys can see, we have different concentrations of reactants and products. So the ratio of those two needs to adjust in order to keep K at 4. So what we do is we say, okay, what we have is K is equal to x squared over 2, and that is gonna equal to 4, and this is at equilib number 2, and right here I'm just going to say, what happens if I double the concentration of my reactant? So we are increasing the concentration of our reactant there, and I just made that up and said, okay, we'll just assume that we doubled it. Okay, so it went from 1 to 2. Now, we need the K to readjust so that it is 4. And on top, I didn't just put x, I put x squared because we've got this square up here. So x is the concentration of NO2, and that 2 up there is the 2 that's right here, okay? So you guys could just replace x with concentration of NO2. All right, so that means that x squared is equal to 8. And x, if we do the square root of 8 on our calculator, would be equal to 2.83. And that is the concentration of, NO2, not N2O4, NO2, right there. So at our new equilibrium, we have a concentration of N2O4, our reactant, of 2. And the concentration of our product is equal to 2.83. Now, if we backtrack a little bit and we look at the original equilibrium concentrations, the concentration of our reactant was what? Was 1. Okay, so that's up here. So concentration of N2O4 is equal to 1 here. And that makes sense because we said it was originally 1 and we doubled it to 2. Okay, and you guys can see in the graph how we're increasing the concentration of N2O4. And then the concentration of the product here. This is equal to the concentration of NO2 squared, and I got that from right here, okay? So that would mean in order to get the just plain old concentration of NO2, I'd need to take the square root of that. So the square root of 4 is what? The square root of 4 is 2, so the concentration of NO2 here is 2. Okay, so we want to get to the concentration of NO2 instead of the concentration of NO2 squared. So we have to take the square root of both of those. Okay, so we have the concentration of NO2 is 2 here, and then at the new equilibrium, after you dumped in some reactant, we did a bunch of math on it, whiz bang boom, and we found out that at the new equilibrium, the concentration of NO2 was 2.83. So you guys can see that the concentration of your product increases when you increase the concentration of your reactant because the system is establishing a new equilibrium, and the new equilibrium is keeping the same K. It wants to stay with a K of 4. Now that was a lot of math just to say that when you disturb an equilibrium, it's going to reestablish a new equilibrium with the same K. Okay, moving on to the next slide. So what happens if we add product? So we have the same exact reaction here, but instead of dumping in reactant, we dump in some product. So we've got our equilibrium established here. So there was a reaction that happened already. Okay. So we had a reactant that made product. It established an equilibrium. It was all nice and happy. It was attending yoga class on Mondays and Wednesday nights. It was feeling really balanced. And then we come along and we're like, ha 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 ha, we want to disturb your equilibrium. We're going to dump in some product. And the system says, I've got way too much product around. I have to do something. I am very disturbed. I got to take care of this situation. And in order to get rid of its excess product, it's going to do what? The equilibrium is going to shift left. So we're going to shift towards the reactant side. So we're reactant favored for a while. And the product will start turning into reactant, and you guys can see right here that the reactant concentration increases, and that's going to happen until it can reestablish equilibrium. So it's going to have a new equilibrium over here, And what can you say about the K for equilibrium 1 and equilibrium 2? The K will be the same because the system will shift things around to keep K the same. Now that doesn't mean the concentrations of N2O4 and NO2 are going to be the same. They're not. They're just going to have the same ratio, okay? So you're going to have a ratio of product to reactant that gives you the same K. Anyways, the point of this slide is to show you that the reaction will shift left in order to minimize this disturbance. Now, what happens if we change the pressure or the volume of the system? So what we were talking about in the previous two slides was adjusting the concentrations of different reactants or products, but what if we change the pressure or the volume? So let's take a look at this reaction where we have nitrogen gas and hydrogen gas, and it forms ammonia gas. Well, on the reactant side of the equation, what you have is 4 molecules of gas, or you could say 4 moles of gas. And what you have on the product side is 2 molecules of gas, or 2 moles of gas. So if you increase the pressure on this system, or you start to decrease the volume that the gas molecules have to float around with, the reaction will shift to the side that has fewer gas molecules. Because if you have fewer gas molecules, you're taking up less space, and that's less stressful. That's just like if you think about if you live in a 2-bedroom apartment, what's more stressful? If you're living in a 2-bedroom apartment with 12 people or 2 people. So the equilibrium will shift to the side where the stress is relieved. Now in our particular equation, we've got 4 moles of gas on the reactant side and 2 moles of gas on the product side. So if we decrease the volume, if we give these gas molecules less space, you're going to get a shift to the right. And because that's the side with the fewer gas molecules, so it's going to be product favored when you do that. So what happens when we decrease the pressure? If we give the gas molecules a lot of room, well, gas molecules, they like to expand to fill the space that they have. And what's easier to expand and fill the space with, 4 moles of gas or 2 moles of gas? Well, it's going to be 4 moles of gas. So if the disturbance is you get a lot more room or a decrease in pressure, your gas molecules will shift to the side of the reaction where there are more gas molecules. So you get a shift to the reactant side here, or you get a shift to the left, or it's reactant favored. There's a bunch of different ways that we can say that. So more room and less pressure, you're going to have more nitrogen and hydrogen gas molecules around because it's easier to fill that space with more gas molecules. All right, what happens when we add or remove heat? So this is going to be interesting because we have both endothermic reactions and exothermic reactions that we have to talk about. Now remember, endothermic reactions are going to be reactions that suck up heat, not reactions that give off heat. Exothermic reactions are reactions that give off heat. So in an endothermic reaction, you're going to see plus heat on the left-hand side. Now, usually we don't write plus heat in our equations because it's not a molecule or a compound, but sometimes you'll see it when you need to talk about it, when it's a subject of whatever you need to discuss. So looking at these endothermic reactions here, we're going to treat heat just like it's one of the reactants. So we're going to put N2O4 plus heat, and that's going to give us 2 NO2s. Now, if you add heat to this system, that's just like adding more reactant to the system. And that means that our equilibrium, we're going to shift to the right. Okay, so our system is going to do a shift toward product there. Now, what happens if you cool the system down? Well, if you cool the system down, you're removing heat, and the system says, oh my gosh, where's my heat going? I'm freaking out. How do I adjust this? How do I come back to a new normal? Well, probably to try to replace the heat that it lost. So how do you do that? Well, you do the reverse reaction, so you start to replace some of that heat. So we say that there's a shift to the left, or that that's reactant favored. All right. If we want to look at what's actually happening with N2O4 and NO2, here it is. So at a low temperature, if you guys can see that, it says minus 75 degrees Celsius. At a low temperature, that means you're removing heat. And the system says, oh my gosh, I'm freaking out. I have to replace that heat that I'm losing because I want to come back to a new normal, a new equilibrium. So we get a shift to the left, and we get a lot of N2O4, which is a colorless gas. And if we add heat in, so say we add heat in, the system says, whoa, I got a lot of heat here. How do I take care of that? Well, I get rid of some of that excess heat by reacting it with N2O4, and that means that we're getting a shift to the right. And if we give a shift to the right, then we get a lot of product. And our product molecule, NO2, that gas is brown, and you guys can see that right there in that tube, and we have a temperature there, a positive 26.2 degrees Celsius. Kind of interesting, huh? All right, so what happens if we have heat on the product side? So we've got some exothermic situations here. So these ones are always kind of weird for students. So it's kind of an easy concept that you put one reactant with the other reactant and you make some product and you make some heat. And what will happen in the lab? Well, your beaker will heat up and you'll feel it, so the beaker will get hot. But what happens if you do that reaction, you come to equilibrium, and then you start heating it up? Well, if the reaction is at equilibrium, it has a certain amount of heat that's hanging around. But if you heat it up, it freaks out and it says, whoa, I've got too much heat here and I need to get rid of it somehow. And the way that I get rid of it is I react it with ammonia, which is NH3, and I'm going to shift to the left. So we have a reactant favored shift there. So equilibrium shifts to the left there, and it makes more nitrogen and hydrogen. Now what happens if you let this reaction of N2 and H2 that makes ammonia come to equilibrium? It has a certain amount of heat hanging around, and you start cooling the system down. So you throw it on some ice. Well, that means that you're removing the heat. You're taking the heat away from the system that it's used to. And the system says, whoa, I'm getting kind of cold here. I need a jacket or something. What do I do? Well, it's going to try to replace the heat that it's losing. And the way that it does that is it takes N2 and H2 and it makes some more ammonia, because when it makes ammonia, it also makes heat. So it's trying to replace that heat that it's losing. So you get a shift to the right. So you get a product favored shift there. The equilibrium shifts to the right. Okay, what if we throw a catalyst in there? Well, the catalyst is going to provide the reaction with a different way to happen. And usually it's a more efficient mechanism. And you'll talk about mechanisms if you go on to take organic chemistry. You'll do tons of mechanisms. Now, for us, we just say that it speeds up the reaction by lowering the energy of activation. So it gives our reaction an alternative pathway to go on that has a lower activation energy. And what happens is we get the same ratio of products to reactants at our equilibrium. We don't get a different ratio of products and reactants at our equilibrium. We just get there quicker. Okay, we get to our equilibrium quicker. We don't affect the position of the equilibrium. Again, we don't affect the product to reactant ratio. We just get to the equilibrium quicker. The K is the same. So the original reaction will take a long time to get to the equilibrium where it has a certain K value. And the reaction with the catalyst will take a shorter time to get to that equilibrium with the same K value. So if it takes a long time without the catalyst and the K is equal to 5, with the catalyst it'll take a short time to get to that equilibrium, but the K will be what? 5. Yes. Okay. So let's do some questions. So the question says you've got 2 SO2s and you're reacting that with an oxygen molecule, and it's going to give you a couple of SO3s, and it says this is exothermic. So we're going to have to write plus heat somewhere. So the question is, do I write plus heat on the reactant side, or do I write plus heat on the product side? Now, don't complicate this too much. You're not going to change any of the reactant or product molecules or any of the coefficients or any of the subscripts. You just need to know whether you're going to write plus heat on the left-hand side or plus heat on the right-hand side. Now, think about this as is. When the reaction happens, when SO2 gets together with O2 to make SO3, you have an exothermic reaction. So is heat going out when this reaction happens, or is heat being consumed when this happens? It's going out. It's exothermic. Like an insect has an exoskeleton, a skeleton on the out-hand side. So on the out-hand side, on the outside. Okay, so we're going to write plus heat over here because when this reaction happens, we produce SO3 and we give off heat. Okay, now if it was endothermic, we would write plus heat on the reactant side because while you're consuming SO2 and O2, you would be consuming heat also. Okay, so now that we've got our heat written on the correct side of the equation, how will each of the following changes affect the equilibrium concentrations of each of our gases once equilibrium is reestablished? Okay, so that's a fancy way of asking which way will the equilibrium shift if we disturb our system in ways 1 through 8. Okay, what happens if you add more O2 to the container? So you're dumping a bunch of reactant in there. You're adding O2. So the system's going to freak out and say, oh my goodness, we've got too much O2. We have to get rid of this somehow. How do we get rid of it? Well, you get rid of it by reacting it with SO2 and making SO3 and heat. So that means that the reaction shifts to the right. Okay, so our shift is product favored. Now, what happens if we remove SO3? Okay, so we're taking our SO3 and we're removing it. Well, the system freaks out and it's like, oh my gosh, someone stole my SO3. I need it back. So it needs to make some more. It wants to replace what was stolen. Like if someone comes in and steals your TV, you want to get a new TV. Okay, so you're going to do whatever you have to do to replace your TV. So our equilibrium is going to shift to the right. We're going to get a product favored shift there because we want to make some SO3. So the SO2s and O2s will get together and make some product. What happens if we compress our system, if we compress the gases? So we have to look at how many molecules of gas do we have on each side. So over here on this side of the equation, we have how many gas molecules? We've got 3. We've got 2 SO2s and we've got 1 O2. So they're all gases, you guys. And over here on this side, we have how many SO3s? We've got 2. Okay, so I'm going to compress the container, so I'm adding pressure or I'm decreasing the volume. So your system has less room. So what side am I going to shift to? I'm going to shift to the product side because the product side only has 2 moles of gas. And if you've got less space, you want to shift to the side where you're taking up less space. Okay, so number 4 says, what happens when you cool the container? So when we cool the container, we're sucking off our heat, stealing the heat. And the system says, oh my goodness, I'm getting really cold. My heat took off. I need to replace my heat. And how do I get more heat? Well, you have to react some SO2 and O2 and shift to the right-hand side. And along with the heat you're making, you get some more SO3. So we get another shift to the right. And at this point, you're thinking, oh my goodness, there has to be a shift to the left somewhere because she keeps shifting this to the right. Don't let that fool you, you guys, especially when you're taking an exam. If you have 4 answer B's in a row, go ahead and put a 5th answer B if that's the answer you're getting, and don't worry about it. Okay, number 5, what happens if you double the volume of the container? So you give this system a lot of room. You're like, ha-ha, you now live in Montana, where there aren't very many people. You have a lot of room. Well, again, on the reactant side of the equation, we have 3 moles of gas, and on the product side, we have 2 moles of gas. So if we give the system a lot of room, which side is it going to shift to? It's going to shift left because you have 3 moles of gas on the reactant side and only 2 moles of gas on the product side. So if we shift to the left, we've got 3 moles of gas to work with, and it's easier to fill our container, which gases like to do, with 3 moles of gas than with 2 moles of gas. Okay, so what happens when we warm the mixture? So when we warm the mixture, we're adding heat. And just treat heat like it's a reactant or a product, even though it's not a molecule or compound. So you're adding heat in there, and the system says, I'm overheating. I need to get rid of this heat. So how does it get rid of the extra heat? Well, it reacts it with SO3, and we have a shift to the left. Okay, so number 7 says, what happens when we add SO3? So we're dumping product in there. Well, if we dumped product into the system freaks out and says, I got too much product here. I gotta adjust and do something to get rid of some of this product. And the way it does that is it grabs some heat and it shifts over to the reactant side. So we get a shift to the left or a reactant favored shift. And what happens if we add a catalyst to the mixture? So if you guys go back and look at the catalyst slide, it says it does not affect the position of the equilibrium. So if you only have SO2 and O2 at the very beginning of your reaction and you put a catalyst in there, the catalyst will allow you to get to an equilibrium situation where you have constant concentrations of SO2, O2, and SO3 quicker, okay? But when you have a catalyst in there, it's not going to shift the equilibrium either direction. It's just going to allow you to get to an equilibrium quicker. So there is no shift here. All right, you guys, that is the end of chapter 6. Yay! See you next time. Bye-bye.